Assalamu alaikum, dear students. Today we are going to discuss the nucleophilic aromatic substitution, and in this we will discuss the SNAr mechanism. So first of all, what is nucleophilic substitution? The aromatic rings are nucleophilic. Electrophiles attack them, and typical aromatic reactivity is to undergo electrophilic substitution. Normally, the normal reaction for an aromatic ring is the electrophilic substitution because the aromatic rings are nucleophilic. In general, nucleophilic substitution of aromatics halide do not happen. Why not? The question arises that why the nucleophilic substitution doesn't takes place in the aromatic rings, because the reactions look alright, and if the ring was saturated it would be alright. If it was a normal saturated ring, so then there was no problem with the nucleophilic substitution. But this is an SN2 reaction, so the attack must occur in the line with the carbon and bromide bond, or the carbon and the leaving bond from the back, where the largest lobe of sigma orbital lies. That is perfectly alright for the aliphatic ring, because the carbon atom is tetrahedral and the carbon-bromine bond is not in the plane of the ring. There will be a problem in the ring from the backside attack. And how? Like if you see here, in the aliphatic ring, the backside attack is here, and if you see, the line of attack is not in the plane of the ring. The line of attack is in the plane of bromide, but not in the plane of the ring. And a nucleophilic substitution can occur in the ring. But in the aromatic compound, the carbon and leaving bond, bromine bond, or the carbon and leaving group bond is in the plane of the ring, as the carbon atom is trigonal. To attack from the backside, the nucleophile would have to appear inside the benzene ring and invert the carbon atom is observed way. This reaction is of course not possible here. To attack the bromine, the carbon must enter the bromine and to renew the bromide, and this is not possible in the case of benzene. The SN2 at the sp2 carbon doesn't occur. If SN2 is impossible, then what about SN1 reaction? This is possible but very unfavorable unless the leaving group is an exceptionally good one. Theoretically it is possible, but it is very rare and will occur in the case when the leaving group is exceptionally a good leaving group. And again, if the leaving group is a good leaving group, it will result into phenylcation. It would involve the unaided loss of the leaving group and the formation of an aryl cation. All the cations as intermediate in this SN1 reaction are planar with an empty p orbital. This cation is planar, but the p orbital is full. It is part of the aromatic ring, and the empty orbital is an sp2 orbital outside the ring. Here, all the other that are inside the ring, they are planar, but this sp2 is outside the ring. Under normal conditions, the reaction should proceed as the base that will attack the carbon, and the double bond will be stabilized with this oxygen, and then the fluorine will leave the compound and we will get a substitution reaction. But in the case of benzene, it is not similar like this. Having two more double bonds in the ring which create the conjugation in the ring. So here an addition will occur and the double bond will be migrated here to the carbonylic carbon, and then elimination will occur and the fluorine will be removed. SNAr, substitution nucleophilic aromatic. The mechanism involves addition of nucleophile followed by elimination of the leaving group, the addition-elimination mechanism. It is not necessary to have a carbonyl group. Any electron with drying group will do. The only requirement is that the electron must be able to get out of the ring into this anion stabilized stabilizing group. This is so that any group, it is not necessary that there should be a carbonyl like that was in the previous reaction. Other group which can stabilize are also possible, like here the nitro. First, the base has attacked the carbon and there is an addition, and the electron has gone out of the ring, form a double bond with the nitro group, the nitrogen, and then again is the leaving or removal of the leaving group, that is chlorine here, and we get an elimination. So it is an addition-elimination reaction. A typical nucleophilic aromatic substitution has an oxygen, nitrogen or cyanide nucleophile, a halide for leaving group, and a carbonyl, nitro or cyanide group ortho and or para to the leaving group. So there must be a stabilizing group that may be carbonyl, nitro, cyano at the ortho or para position to the leaving group, that is halide. It's para here. And the base or the nucleophile must have an oxygen, nitrogen or cyanide nucleophile. If there are two activating electron with drying groups, they are better than one, and dinitration of chlorobenzene make a very electrophilic aryl halide. If we have dinitro compound, it will be easily substituted, like here 2,4-dinitrophenylhydrazine. What is the intermediate in the addition-elimination reaction? When reactions are carried out, a purple color appears in the reaction mixture and then fades away. In some cases, the color is persistent and thought to be due to the intermediate. Here, delocalization of the charge in the intermediate. The continuous delocalization. Here is an example of RO attacking a nitrated aniline. This intermediate is persistent because neither potential leaving group is a very good group. So it may be present after the reaction because the leaving groups are not good groups, good leaving groups, and maybe that may be present, the intermediate may be present for a long time, and so the color will be persistent. What is the nature of this intermediate? Well, in essence, it is an anion delocalized over 5 sp2 hybridized carbon of a 6-membered ring. The sixth, the point at which the nucleophile attack, is sp3 hybridized. Here it converts into sp3. It is possible to make a simple homologue of such a species by deprotonating cyclohexadiene. Delocalizing the anion generates the 3 structures. We can delocalize this anion into different position, from here to here, para position, and from this para to this meta position, and we can get 3 different structures. The mechanism is of 2 steps. First step is the slow step. In this, the aromaticity is disturbed, and this is the rate determining step. In the first step, when the nucleophile attack and the aromaticity is disturbed, this step is accelerated by electron withdrawing groups through inductive effect, and this is accelerated by the electron withdrawing groups. Fluoride accelerates the first step through its inductive effect. It is the most electronegative element of all, and it stabilizes the anionic intermediate, assigning the acceptance of electron by the benzene ring. As fluorine or fluoride is the most electron withdrawing group, so it stabilizes the attack that a nucleophile can attack the carbon easily, as it is withdrawing the electrons from the ring. And this one is the rate determining step, the attack of the base, of the nucleophile, or the addition of the nucleophile. The second step is the fast step. In this, the aromaticity is restored. In this step, the leaving group is removed from the substrate. How good a leaving group it might be doesn't matter. The rate of the second step, the step where leaving group leaves, has no effect on the overall rate of reaction. This is a fast step, but this is not a rate determining step. So the ability of the leaving group doesn't affect the overall rate of the reaction. Nucleophilic aromatic substitution. Aryl halides with electron withdrawing substitution ortho and para react with nucleophiles. Those aryl halides which has electron withdrawing substitution on ortho and para position react with the nucleophiles, like here ortho, and we get this adduct. The similar is case here. For addition intermediate, that is called Meisenheimer complex, that is stabilized by electron withdrawing groups, withdrawal. And the halide ion is lost to give aromatic ring. This substitution, when the electron withdrawing groups are on the meta position, so the reaction, no stabilization of charge by nitro group, and the reaction is not possible. Nucleophilic aromatic substitution. Look into this reaction. It's possible that the amine will replace the chlorine, and we will get 2,4-dinitroaniline. A nucleophile replaces leaving group on the aromatic ring. This is an addition-elimination reaction. Electron withdrawing substituents activate the ring for nucleophilic substitution. As we have previously discussed that the fluorine is a strong electron withdrawing group, so it activates the ring for the nucleophilic substitution. Mechanism of nucleophilic aromatic substitution. The first step is the attack by hydroxide gives a resonance stabilized complex. This is the first step. And it gives a stabilized complex which is resonance stabilized, and we are getting these different resonance structures. The second step is the loss of chloride, and this gives the product here. And sometimes the excess base deprotonates the product here. We will get a phenoxide. The activating anion stabilizing substituent. The nitro groups are used extensively because they are the best at stabilizing the anion intermediate. Others that work include carbonyl, cyanide, and sulfur-based groups such as sulfoxide and sulfones. The nitro group is considered as the best for stabilizing the anionic intermediate. All the compounds react more slowly than the nitro compound. The great electron withdrawing power of the nitro group is responsible for the greater reactivity. Here, these are the group. This is the red determining step. The nucleophile has attacked the benzene ring. And then the first step, the bromine has left, and we have this nucleophile piperidine is added to the ring. There is a comparison. If we consider the nitro group as 1, the activity of the other groups are like this one, 1 by 18, 1 by 32, and 1 by 18. So this will activate the ring by this ratio as compared to the nitro group. The nitro groups ortho and para to the halogen stabilizes the intermediate and the transition state leaving to it. If the nitro group is present at ortho or para position, so it stabilizes the intermediate and the resulting transition state. Electron withdrawing groups are essential for the reaction to occur. There must be electron withdrawing groups for the proceeding of the reaction, but these electron withdrawing groups should be at the ortho or para position of the leaving group. The activating anion stabilizing substituent. Nitro is the best activating group, but the others will perform well, especially when combined with a fluoride rather as a bromide as the leaving group. As we have earlier discussed that fluoride is stabilizing the ring due to its higher electronegativity. The trifluoromethyl group works by using only its powerful inductive effect. To summarize, an anion stabilizing electron withdrawing group ortho or para to a potential leaving group can be used to facilitate nucleophilic aromatic substitution. Here, 97% yield, 59% yield. Thank you very much. Thank you.